Hi there, and welcome to today's webinar. I'm Mark Bauer. I'm the Vice President of Product Management here at Anjuna, and I work a lot with our customers on this area that we're going to talk about today, which is confidential computing, particularly with a focus on a very hot topic today, which is related to mitigating AI risks, especially when you're running these kinds of workloads in the cloud. So today we'll include an introduction to confidential computing, and then we'll dive deeper into the world of AI risks and how confidential computing can apply. So when we actually look back a few years now, in fact, over the last couple of decades, we saw the introduction of technologies like TLS or HTTPS that has ultimately enabled us to connect the world in a very secure way, protecting data as it moves and is shared across different ecosystems. And today, we take this for granted. This is a technology that maybe 20 years ago was not quite the case. We might have found that we had websites and so on where we were entering passwords or where we were entering things like our credit card details, and that might have been protected with TLS, but the rest of the traffic wasn't. And that's because the technology was a little challenging, had high overheads, but today those problems have been solved. And even websites that don't really have any kind of sensitive information use HTTPS today to provide trust and authenticity, so you know who you're dealing with. So this is a technology that has made a profound change on the world today, and it provides us with that secure connectivity. Similarly, firewalls, also introduced over the last couple of decades, allowed us to connect businesses together. Essentially, it allowed organizations to put themselves up on the internet with some degree of isolation to allow them to conduct and engage on an electronic and digital basis without massive risk. And once again, today, firewalls are part and parcel of almost every piece of infrastructure that we work with, whether it's on premise or in the cloud, or even at home. We use firewalls today to isolate our own networks from this wider infrastructure. And so confidential computing is a technology that is in this realm. It is an enabling technology with profound consequences, which will change the way that we compute, not just today, but long-term into the future for almost every application and workload that's foreseeable. It solves two major problems. Number one, the very long-standing problem of protecting data as it's used, that is in memory and in the processors themselves, and also to solve that problem of trust. How do I know that what I'm going to be computing on truly has not been tampered with and can be trusted with the most sensitive information or even the most general application? So without this kind of technology, essentially data and code that operates in memory today is largely unprotected. And obviously that includes all manner of code and data, but some very sensitive information that if compromised can yield all sorts of kinds of risks to organizations and enable attackers to do untold damage. That includes things like credentials, perhaps intellectual property like artificial intelligence models, encryption keys that might be used to decrypt highly sensitive information, code, intellectual property, all manner of secrets and so on. And of course, the other challenge when we think about computation today and running applications in infrastructure, we're all keen to use zero trust principles to make sure that we establish trust before we start using infrastructure or we allow users and organizations to connect. But the question is, how do we really trust that compute is truly trusted so that we can use it with sensitive data before it's used? And today, we often do this by looking at assessments on paper that might have been conducted at a particular point in time, but is that really telling you that things like the hypervisor hasn't been compromised, the BIOS, the firmware, the operating system, or the application itself? And supply chain breaches have proven that that is a real challenge. So confidential computing is this hardware-assisted security technology that is in the processors themselves and allows organizations to create a walled garden around whole computational applications and data. And this puts the control of this infrastructure within these processors back in the hands of the data owners and the application owners themselves. And when you think about the cloud, that's been a challenge in itself. This shared responsibility model often puts the liability back on the data and code owners, but certainly doesn't give you the control and the transparency over absolutely everything going on in the cloud. And this is why we see organizations that are often struggling to adopt it. And without confidential computing, we actually have a cyber resilience gap. In fact, this is a study that is worth reading that was from earlier this year from the CISA organization, the Cybersecurity and Infrastructure Security Agency for the United States. And this was an exercise that was conducted by a red team. So essentially the good guys looking at an organization and attempting to break into it through vulnerability exploitation and attack mechanisms. So in this particular case, this red team pulled decryption keys from active memory, used those to go after a credential database, which allowed them to then gain wider access to all sorts of other types of infrastructure, as illustrated here. And so while this was a red team going after a large mission critical piece of infrastructure to enhance resilience and discover vulnerabilities, it's a common problem that has been plaguing the industry for many years, this issue that memory has largely been unprotected until recently. And in fact, this type of attack is all too real. And one has to really commend Microsoft for being fully transparent about a recently reported scenario that had exactly this type of compromise impacting US government agencies. So if you haven't been following the news, this is worth double clicking on, and I would encourage you to read the Microsoft reports here. But essentially what happened was that a production system within the Microsoft infrastructure crashed, as many applications do from time to time, and as a consequence it produced a memory dump. Now ordinarily the memory dump was supposed to have been scrubbed of sensitive information, and in this case that didn't happen. And so what was present in the memory dump were production keys, and as that memory dump was then moved to the corporate network, that's where a compromise took place. Once there, the compromised data was used to exploit further vulnerabilities in the ecosystem, ultimately resulting in the compromise of sensitive data, in this case, emails and so on, particularly targeting US government agencies. So as you can see, there was data in memory that ultimately ended up with a compromise that presented a horizontal attack across very sensitive organizations. And so this is just one example of the scenario that we've outlined, where memory and data protection have not really protected ultimately something sensitive like a key. So what I'm going to do now is actually switch gears and illustrate this in practice, and we'll actually look at this problem overall. So let's jump in here. So the system I have on the right is an AWS platform, so pretty standard terminal, probably running in US East somewhere, and running classic Linux ecosystem. So this is effectively just a raw AWS system that I'm accessing here on the right. And what I'm about to run is a very powerful key management system. It's a leading product. We're partnered with this organization. This is a powerful key manager that is often used to manage secrets and so forth in organizations. And like any piece of software running, whether it's on premise or in the cloud, on regular computing, then it is vulnerable in terms of the operating memory, as you'll see. So what I'm going to do here is just fire up the, in this case, the HashiCorp Vault system. And you can see this on the right-hand side. This is how Vault is now booted. And I'm going to issue a command over here, Vault status. So let's have a look at that. So now I know that it's running. We can see the version number and so forth. So I'm going to put a secret into it here with these Vault commands. And so I pop the command on the command line, run it, and now we have inserted a key into the Vault system. So I'm going to also now prove that I did that by getting it back out. So nothing particularly tricky about these very common operations to put secrets inside the vault. But as I've said, like any application that is running today, think of your databases in your environment, your applications terminating TLS and decrypting traffic, your applications pulling records off a file system, maybe decrypting it into memory, or even just data that's in the clear in memory that isn't going into storage. All of that is vulnerable if there is a compromise of that memory environment. And that's exactly what I'm about to do here. So all I'm going to do is grab the process ID for the Vault process running in this AWS Linux system on the right. I'm going to issue a gcore command, which is basically a Linux command to dump memory and stop the application. And so this will produce a file of the memory contents. Now here I'm obviously playing the role of an attacker. Imagine that I'm a curious SRE. Maybe I'm elevated malware that has high levels of privilege, and I'm able to run those same kind of commands or something very similar to gain access to memory. So as I pull that memory out, what I'm now going to do is parse it to recover sensitive data. And so I'm actually going to be using a simple script to identify and recover sensitive data here. So let's actually run that. So you'll see on the right-hand side, I've processed this memory dump, and you'll notice that now this has given me access to essentially a master key out of the dumped memory. So again, this is no fault of the HashiCorp system. It's a fault of the fact that memory is ultimately accessible with the right level of privilege, which can happen for a number of reasons as I've described. But with this information, I can potentially then decrypt other things. And so similarly, if I was running a database and I dumped memory, I could get active keys out that might have been used to protect columns or tables or other pieces of data. So you can see how vulnerable the memory actually is in this simple example. And we're going to come back and revisit this at the end of this webinar, and I'll show you how this can be mitigated in just a few seconds. And clearly, with the types of breaches that I've described and many others that happen across the industry that plague the news today, organizations are still obviously somewhat hesitant to use environments where they have less control, despite the power and despite the very good security controls actually within. Ultimately, in certain industries, this is also a more acute problem, particularly in financial services or organizations that deal with highly regulated data. They're often hesitant to use the power of the cloud because of these concerns over security, but also just trust and being able to understand precisely exactly how data is processed from the bare metal up when it's in servers that they don't control. So confidential computing on its very surface helps solve this exact problem. It unblocks clouds and provides new levels of control based in hardware to provide isolation and trust for those sensitive workloads when they're moved into public cloud environments. But confidential computing infrastructure is actually quite available across clouds today. But there is diversity of the ecosystem, and there's also diversity of how it can be consumed if you use the native capabilities. At the end of the day, organizations that are looking to embrace this technology want to take it to its full power, and that is not just ticking the box on memory encryption, but to use the attestation capabilities, the trust mechanisms, to provide guarantees over integrity of workloads, so you know that that software supply chain hasn't been compromised. And so when you think of all of these ecosystems here, you've got different chipsets, different architectures, different operating systems, and then infrastructure on top like Kubernetes and so on, and you've got diversity in the clouds, then ultimately to use this in a very ubiquitous way without having to build it yourself, you need a software stack to enable this to be consumed easily, to essentially take applications and run them as is. And that's precisely what we saw in the past when we had the virtualization technology emerge in the Intel chipsets, and we had VMware arrive to deliver virtualization software to make that really powerful and consumable. And today, this is now another of those technologies that revolutionized compute, and we wouldn't think of running anything without virtualization in essence. So Anjuna is a virtualization software for confidential computing across all of those different types of ecosystems, across all of those different types of clouds. So you can simply take an application, container, and run it in a confidential computing ecosystem of your choice, and then expand into that world with Kubernetes to run those enterprise applications at scale on a totally private basis. So this is available essentially across clouds, and the future of confidential GPUs is just right around the corner. And where that will start to enable us to think about confidential AI at completely new levels of scale, to have almost private supercomputing power at one's fingertips. And so this starts to open up completely new things that you can do. So how organizations use this technology today, we see a number of different prominent use cases that unfold before us. The obvious one, the most obvious one, is unlocking cloud transformation. So for those organizations that are still, after decades of cloud availability, been hesitant to move these workloads up into the cloud because they haven't been able to achieve the controls that they've so relied on in the data center for compliance and risk reduction when they move those up into a cloud environment. That's something that is now available. So confidential computing delivers that controls equivalence that lets this process of cloud transformation go all the way to the most sensitive workloads. And this also enables organizations to do things a little quicker as well. And so instead of having to build more complex controls into applications specifically for the cloud risks, confidential computing addresses them head on and allows that faster time to market for applications that are unblocked. Another obvious use case is protecting cryptographic secrets. So keys, secrets, digital signature systems, anywhere where you rely on highly sensitive data to sign transactions, to decrypt content, to enable authentication authorization, precisely the things that the attackers first go for. Confidential computing allows those to be isolated, not just from a key and a storage perspective, but to actually entirely enshroud the operations on those cryptographic secrets. And ultimately, this gives you a huge reduction in the MITRE attack surface of very common vulnerabilities on an instantaneous basis, some 77 of the attacks in the matrix today. And then the last two here, which we see more and more of, is isolation of code and data for things like data sovereignty and zero trust. You can think of confidential computing as a way to achieve zero trust for code and data. It's a very natural fit to zero trust architectures and strategies. And last but not least, and we'll dive further into this, is the confidential AI. And with more and more organizations putting more data and more sensitive code up into the cloud, confidentiality, not just of operations, but of the data itself, becomes absolutely paramount to success. And so we'll dive into this a little bit further in the second half of this webinar today. So first of all, I'm going to talk about a scenario of that cloud transformation, just to put things in perspective. And we're going to visit a kind of a visualization of this scenario, and I'll tell the story of the success of this bank in moving workloads to the cloud that were previously blocked. So in this particular case, this is a large bank that had already moved its customer digital experiences up and into the cloud. And like many organizations, had been reducing the presence of the physical branches across the country. And then COVID hit. And what happened was that more and more users moved to the digital channels as a result, less people going into branches. And so as the number of users started to increase, the web front ends and the IVR systems and the mobile systems scaled out rather nicely. But what was starting to happen was that the core banking systems back in the data center weren't able to keep up with this new online load. And as a consequence, both the cost went up significantly, which is based on a transactional model, and ultimately this meant that the latency for the user experience on the front-end systems also spiked, resulting in customer concerns. And so with the risk of attrition, and with wanting to keep its customer satisfaction scores up, as well as delivering quality services, this organization wanted to move this ecosystem up and into the cloud. And on the other hand, there was regulations in this particular case driving further scrutiny over data in use in the cloud for highly sensitive data like keys and personal data. And so the bank had a policy that any personal data and any keys up in a cloud environment must never appear in the clear. And so that produces a challenge. And so what they did was to utilize confidential computing, in this case with AWS, to encrypt records from the data center up and into this caching tier in a MongoDB system up into the cloud, move those records in an encrypted form up, and then run this caching tier, what we call ODS. It's a design pattern that works often with MongoDB to offload transactions from the core legacy systems like the mainframe. And so with this tier then running in AWS Nitro enclaves enabled with the Anjuna system, this was essentially a lift and shift from the caching systems that were inelastic and on-premise, running in a cloud-native ecosystem, but not able to scale in the same way as you can in the cloud, now able to run entirely isolated in the cloud. So what this did was solve two problems. One was the need for credentials could be eliminated to retrieve keys from the KMS system. So using the hardware roots of trust to effectively authenticate to obtain keys to then decrypt traffic, and then running all of those encrypt and decrypt operations in isolated environments, allowing the banking details to be pushed up to the mobile systems end to end and presented to the user in their devices without exposing that sensitive data in the cloud. And so as this system is now enabled to scale up with an automatic Kubernetes EKS ecosystem, the latency was able to be kept to an absolute minimum while also dramatically reducing the cost on the mainframe itself. So a huge win-win for the business, moving a highly prized workload to the cloud for millions of customers, but also solving that customer digital experience problem using a confidential computing approach. So when we start to think, though, of this next phase that most organizations are in, which is exploring AI, be it generative AI or exploring models to run optimizations on data sets, to explore new things, to be faster with decisions, to be more accurate in pinpointing business opportunities, we start to run into an immediate set of new complex problems. And this is not just about encrypting data at rest or in transit. AI, particularly generative AI, starts to introduce completely new things. With generative AI, you're able to create brand new data from original information. And so the process of creating that is highly prized and highly sensitive, as is the data that goes into it, as well as the data that comes out. And as we've seen, there's various reports, including these from Gartner, that shows that organizations today have already suffered from a whole range of breach risks with the AI that they are exploring. And with generative AI, you've got everything from the data that could be highly sensitive, you've got the models, and you have also data that comes in and out, the queries, for example. And then you have operational ecosystems that sit around this. And so many organizations today have started to explore AI perhaps with non-sensitive data. But when you start to think about the power of things like large language models, you've really got to think in a very different way. You're now required for security and for also just operating this on a best practice basis to think about protecting the code and the data and the entire computation as it executes across all of the ecosystems that sit underneath, be it from the databases, those vector databases where models and data are stored, through to the actual weights and balances of the models themselves. So we've been exploring this here. And if you start to look under the covers of things like the large language models that many of you are probably experimenting with today, and you start to attack them through active memory exploitation, there's all sorts of things that you can uncover. So you typically find lots of very powerful data sets stuck in Redis caches. You even find chat history of queries and so on. This is kind of obvious stuff. But when you get down to the AI models themselves, you're getting into the data in the models, the weights and balances, all sorts of model parameters. And even if those are perturbed in just a tiny way, that might create bias in outcomes that could be highly impactful. Imagine you're using a model to determine the market price for goods. If that is perturbed, then you might be losing out on revenue. If you're using these types of technologies to do really sophisticated things like assistive surgery recommendations, then data integrity, code integrity, and execution integrity are paramount to people's lives. And so security enters a completely new realm, especially when these are attackable through things like memory. So confidential computing does allow organizations to address many of the AI risks. And these span a number of different areas. First of all, there's protecting the model itself. And not just when you're running the model, we'll talk a little bit about that later. When you think about a model, you might be building an AI system to consume in your business. Maybe it's a service back to the business, for instance, so they can run different workloads, put different data sets in and explore different things. But you might be using models from third parties. And in many cases, that model represents IP. You may be developing models yourself that you want to push to your customers. And so being able to secure that and distribute it and control it with almost a rights management solution, it's where confidential computing comes in and enables these kind of leasing concepts with powerful controls in hardware. Then we've got the notion of training. And so the quality of models and the quality of the output is going to be highly dependent on the quality of the data going in. And training, as if you've read many of the reports, if there's any perturbation of training data, then we may end up with models that have an inaccurate representation or even can be attackable because of the nature of the training information that's gone in. And so confidential computing can be used to bind a model environment to a data set so that you can have end-to-end protection and trust over that process to allow you to control precisely what data is used for training and as input. Then we've got the actual execution, the model operations, and this becomes very important. When you think of a model that is actually making inference outputs and we're seeing results, then the state of the model and the state of the training, the state of the data, the state of the operations will be important to have trust in, so that you know that at certain points in time, when data comes out of a model, it has a trust footprint behind it. So knowing that there was integrity over the processes, being able to do that in hardware is a very profound way to solve these kinds of problems. And so this starts then and get into that operation and integrity of AI. So we're seeing this at work today. We have organizations exploring confidential AI, be it in banking, be it in SaaS organizations, be it in life sciences companies. But here's an example of one that you're probably familiar with. So when you're in some countries, you operate your motor vehicles on roads and you're supposed to stay within the speed limits. And so in many organizations or many countries, you have these things called average speed cameras. And what they do is they take snapshots of your vehicles as they enter roads and they recognize them. And as you exit the road, it also recognizes the vehicle and then computes the speed. And in some places, there's automatic tickets. And so in this particular scenario, this organization, essentially a kind of a government agency that partnered with a large telecom, had feeds coming from the cameras with cars going into a data center with AI processing for all of those good things, and then issuing citizen notifications about speeding. And before you knew it, the idea was to get a speeding ticket, have good customer service on that, but before you essentially got home. So while this might not appear great from a citizen perspective, it's great from a government process perspective. But the challenge was that as more and more load was on these dedicated racks, the only way to scale was to add servers, which is extremely expensive. And so what was happening is that customer notification system wasn't able to keep up and resulting in kind of disappointing experience. So by moving this up into the cloud, using confidential computing to protect the data all the way, essentially from the cameras all the way to the enclaves running the feature extraction, and then passing that data up to the GPUs, this organization was able to scale so that they could keep that customer experience on track and rapid, again, without having to invest in further data centers. And so as a result now, not only has this organization enabled this new way to address an AI workload in the cloud on an elastic basis at least cost, but they're also able to think about now leasing those models to other organizations around the world to repeat this success in other countries and essentially monetize the IP that they have created. So when we step back and we think about confidential computing, it's not just about ticking that box for memory protection today and running things in a basic confidential VM. It's ensuring trust. It's ensuring isolation. And it's doing this in a way without having to make major changes to application or code, even with complex applications like Kubernetes-based apps. It's also about protecting not just the data in use, but to secure it from inside the enclave so that any data that comes out that's encrypted within stays protected end to end. And this is a critical part of confidential computing. It's about protecting the data from within these confidential ecosystems. So those databases that had compromisable keys, for instance, operating inside an enclave so that the data that's stored outside remains encrypted with keys only accessible inside that hardware isolated ecosystem. And then when we start to think about the operation and orchestration of this and how we manage secrets injection, typically today when organizations launch apps, they put tokens and they put sometimes secrets into environment variables or files, and then we hope that those don't become compromised. That's definitely not a good idea, but it's been difficult to solve. It's the secret zero problem. So you need a way to eliminate that using the hardware roots of trust so that credentials and secrets management can become essentially a thing of the past for applications operating in the cloud. And of course, at the end of the day, this has to be minimally impactful, just a few percent of overhead, which traditionally with encryption has always been a big challenge. And last of all, for organizations that work in multiple clouds, it's critical that they work, this ecosystem works across them. So that's essentially what we help with, and I'm going to revisit that application that we started with here. So let's quickly take a look at this. So first of all, let's kill that old system off, and we'll start again, and we're going to run it in confidential computing. So the first step is to take the existing application, just in this case, the HashiCorp Vault repo without change, build an enclave image file. And what we're doing here is we're filling in all of those gaps that are there. If you try to do this yourself in AWS Nitro enclaves, you'd have to refactor this application in order to make it run. You'd need to add storage. You'd need to add networking. You need to add all of the subsystems that it expects to run out of the box. That's what we're actually adding here, and the Anjuna runtime, which is essentially like a container runtime inside the enclave, provides all of that. So with AWS Nitro enclaves, just very quickly, the enclave is separated essentially by a hot switch capability that's the AWS Nitro enclave system that isolates CPUs or vCPUs from the rest of the compute instance that connects to EC2. So this is how the enclaves are separated. And then on top of this, depending on the processor, there's memory encryption techniques and so on for further isolation. So this enclave is now almost like an isolated system that communicates with the rest of the world through this little VSOC layer here, which is a high bandwidth network connection. So we're going to run a little proxy that allows the enclave to talk to the outside world. Now we're going to run the application. So I'm going to run the application I just built. So now we are effectively running the Vault system, a powerful key management system inside the enclave, Nitro enclave. So we're going to just check that. So this is essentially, we've proven that what we built, these measurements up here, are what you see down here. So this is part of the kind of integrity process. Let's check that it's running. We now put a secret in as we did before. We'll now get that secret back out. And now the final piece, I'm going to take that role of an attacker and attempt to attack this system. The thing is, I've got no way to attack it. It doesn't exist as far as I am concerned, even though I have the highest privilege. So I can't dump memory. I can't even see the HashiCorp Vault process. The attack that we showed has been completely neutralized. So now I'm immune from many threats that could compromise memory, resulting in all sorts of downstream compromise. So we challenge you to try this yourselves. If you're interested in learning about this, we actually have this demonstration environment. We call it Anjuna Quick Start, where you can take one of the existing apps or maybe even your own application and quickly run it in just minutes in a confidential computing environment. It really is that fast. And you can convert then from vulnerable applications to secured applications in literally minutes. In fact, it's probably seconds. If you'd like to learn more about this with respect to AI, there's a couple of white papers here. We've got some Gartner downloads on our website. Pop over to anjuna.io for info there. And do connect as well. We're more than happy to engage, review applications with respect to confidential computing, look at workshops if you have multiple applications that you want to think about in reducing risk, running AI, or just want to unblock applications going into the cloud. So as said, my name is Mark Bauer. I'm the VP of Products here at Anjuna. Do connect with us, and we look forward to engaging soon. Thank you so much.